So let us start. Hello, I'm Professor Wenzhe from University of Seoul. We are going to start session 2 now, and it's hosted by University of Seoul. The theme of this session is changes and reactions to life in metropolitan area after COVID-19. We have 4 speakers. The first speaker is Professor Heechung from the University of Seoul. She will talk about major policy changes in leading cities around the world. And then Professor Inkyu of University of Seoul will talk about global urban digital model and toy modeling of COVID-19 spread. And from overseas, we are going to hear from Dr. Cuauhtemoc. He is from Singapore, Data Spark. He will talk about latest research and development efforts on the topic of mobile phone data and transportation. Last but not least, Professor Jan-Dirk Schmoecker and postdoctoral researcher Wenzhe from Kyoto University will be making presentation on learning urban mobility and activity patterns with Kyoto case study during and after COVID-19. And after the presentations, we are going to have discussion between 3 people, and 2 of them are from University of Seoul. First, Professor Park Sang-shin, and then Professor Lee In-pyong. And online, we are going to be joined by Professor Kim Tae-hyung from Seoul National University. So I have introduced you to the panels, and the chairperson of Korea Land Studies Association will be making a brief welcoming remarks. Hello, I'm Kim Hyung-seok from Korea Planning Association. Congratulations on Korea Planning Association. And when COVID broke out last March, because of the infection risk, we could not meet, and we believed that the cities will be decentralized, but the cities have not decentralized. More companies are moving into Seoul because Seoul is the center of innovation. So we are seeing more and more companies centralized around the Seoul metropolitan area. And as the population of Seoul declines, we are seeing the Seoul metropolitan area expand in size. And the gap between the metropolitan area and remote area is widening. With the accelerated digital transformation, innovative companies and innovative industries are converging around Seoul, and mobility renovation is being accelerated with mass-like connection being enhanced around transshipment or transfer areas. Pandemic is also related to climate change, and there is stronger interest in carbon-neutral cities and ways to promote biodiversity and accessible green areas. And Seoul Metropolitan Government is planning to expand green space around the urban area. Whenever there is another pandemic, we need to show stronger resilience and 15-minute smart cities. When COVID-19 broke out, Professor Yuval Harari said that the history will be divided before and after the COVID, and I can now fully empathize with him. And when with COVID, era evolves, we are going to be living in a city that's quite different from what it was before. But the Korea Planning Association and the urban planning originates from many previous theories. We are stuck in the past. Now we have to pour new wine in new bag, and in this new era, we need to create new spatial theories. It's a great honor to be co-organizing this forum along with University of Seoul, and I hope we can have very constructive debate on this theme. I would like to thank University of Seoul, and also I would like to thank Professor Lee Seung-jae for moderating this session, and also Professor Lee Heechung for planning this. He is also a member of the Academic Committee of Korea Planning Association. Thank you very much. Thank you very much. Now we are going to start the presentation. The first presenter is Professor Lee Heejung of Seoul, University of Seoul, and he will talk for 25 minutes. Good afternoon, ladies and gentlemen. I'm Professor Lee Heejung from University of Seoul. Today, I will talk about after COVID-19 urban future. Seoul, University of Seoul, and Korea Land Planning Association have done some academic networking to identify what kind of changes have taken place in major cities around the world: Seoul, Tokyo, London, New York. So over the past 1 year, COVID has made a great impact on our cities, so we are observing and collecting data about such impact. And I will update you on where we are, looking back on the past year, and also shed some light on how our city should cope in the future. So let me talk about the major city data, and also talk about the future urban environment. Around the world, there is huge crisis of pandemic. It is creating new normal. Various digital transformation is taking place, and also it is enhancing and widening social inequality. And we are seeing various problems from cities. And urban policies and urban planning presents us with diverse challenges. And in international seminars, we are always talking about sustainability, inclusiveness, resilience of cities, and city policies and changes. As the chairperson of the Korea Planning Association said that our history is going to be divided before and after COVID-19. And at the center of such change would be the cities. When we look back on the past human history, such experiences give us a very clear message. In the Greek era, typhoid fever led to the collapse of Athens, and that gave birth to an epidemic discipline called urban planning. In the 14th century, Black Death was raging around Europe. That led to major social changes in Europe, and it created new discourse on cities. In the 19th century, cholera became prevalent, and urban planning was connected to industrialization at that period in time. And these were major pandemics that gave rise to such changes in the urban structure. And 100 years ago, Spanish flu has had a huge impact on the world. And Vijay, a new urban scholar, has came up with this glistening, bright city model. And around the world, more than 200 million people have been infected, and millions of people have died, and it's still ongoing. COVID-19 as a new pandemic, how will it change our urban civilization and urban destiny? That's what the entire world is really interested in now. Such urban changes, we need to have an exact understanding of what kind of changes are taking place and respond to them in the most effective manner. I think this is what the experts of our time must do for the future generations of people. Because of COVID-19, our economies have been hit hard, and it is going through major changes. Also, in the social sector, COVID-19 has generated a lot of social issues, and lifestyle is also changing significantly. We are observing social distancing and a new type of social culture called untact, and remote working, remote education are becoming more prevalent. We are now working and being educated and living in an unprecedented environment. Let us now talk about data to find out what kind of changes are taking place in our societies. Today, this is based on the Seoul data added to previous research data in connection with other foreign cities regarding residential, commercial, and leisure areas, and how that is leading to the changes in mobility patterns. So for the past 2 years, from 2019 to today. First is residential space, especially real estate data and the residential environment has a critical impact on our lives. And around the world, because of COVID-19, we are seeing some direct and indirect consequences of the pandemic, and the housing prices have gone up. And in London, the housing prices is gradually going up. And in the case of New York, in the initial period right after the outbreak, the real estate market went down a little bit, but with the pandemic prolonging, people are now believing in the value of good residential environment, and the housing prices have recovered, and generally it is going up. And as you can see in the pictures at the bottom, in Manhattan area, especially the urban housing prices have gone up more than others. Such trend is also found in Tokyo, and overall housing prices are on the rise in Tokyo as well. And another unique characteristic here is that Tokyo, they have 23 districts, but there are other outer areas like Tama-hyun and Chiga-hyun, and the major metropolitan areas have sprawled into outer areas, but relatively the urban housing prices have gone up. But the rent cost in the outer areas have gone up, but the housing prices themselves in the urban area have gone up more than any other areas. Also in Seoul, because of cultural similarities to Japan or for some other reasons, Seoul is showing similar trends to Tokyo. After the COVID-19 outbreak, the housing prices in Seoul is also going up. And when we go outside of Seoul to Gyeonggi province, we are seeing people moving out into those Gyeonggi province areas. The actual housing demand in the outer area of Seoul has increased, but the housing price in Seoul area has skyrocketed. And there could be many reasons for skyrocketing housing price, but it is rising much higher than any other cities. When we think about other cities like London, migration in Korea has declined significantly because inside a country, migration has declined greatly. And in London, the number of people, new migrants, has decreased as a result of the pandemic. And the total number of people moving has gone down. And same thing is happening in the United States. The United States, for example, California shows high sensitivity to change in the number of migrants because in California, they saw a drastic drop in the number of people, migrants from overseas, probably as a consequence of immigration law introduced by Trump administration. And many people are leaving California as well. So overall, the migration in California has gone down. And in the urban area of California, more and more people are moving outside, out of the downtown or urban center area. And also in Tokyo, people are moving out of Tokyo. So outflow pattern is increasing. And we can see that the cities are becoming stronger and getting wider and decentralized. And Seoul, the number of people moving into Seoul has gone down drastically, and more people are moving out of Seoul. And in Seoul, people are moving out into the suburban areas at the outskirts of Seoul because they're looking for lower-priced housing options. We can see that clearly through data. And when we look at the housing price change, as we can see in the graph, before and after COVID, we can see that housing prices have gone up sharply. At first, it was the apartment houses pricing going up, but now even the rental cost is going up. And it is spreading nationwide. On the right-hand chart, compared to the housing price, the rental cost has gone up as well. Even though overall proportion has gone down because of the drastic rise of the housing price, but the housing rental cost has gone up as well. So residential migration after the pandemic is closely related to the decentralization of housing options and working from home and residential migration pattern has created decentralization and expansion of Seoul metropolitan area. And Seoul, Gyeonggi province, they have this edgy state, and wide area or decentralized area is gaining force around the suburb station areas. Regarding the lifestyle, the home office is becoming a common option of working, and people are now increasingly looking for larger residential space because the houses should also function as an office as well. But relatively speaking, in old downtown area, as more and more houses become aged and old, people are increasingly looking for new residential models. And regarding commercial space, commercial and office space in foreign cities, the floating population has declined drastically because of COVID-19, and it is found in all cities. Floating population has gone down and telecommuting has increased. In the case of Taiwan, since they had less impact, they saw less decline in floating population, but other cities, especially European cities, they saw rapid rise in telecommuting. And in the case of Japan, last year, about 40% of the people worked at home, and Japanese houses are generally small, and around the subway station areas, people rented the remote office space, and public sector took the lead in providing such rental office space. As you can see on this graph, in 2000, the number of telecommuters has increased rapidly with the rapid rise in the number of infected people. And residential office has increased, and Zoom or other teleconferencing platform has seen rapid increase in their revenue, and online shopping industry grew rapidly as well. And various online trends gained momentum, and that is clearly observable through the data. And the industries are being structured, and on-demand shopping platform is increasing. And we also have some popular delivery map apps such as Baemin, and delivery culture is expanding. And the online shopping revenue and the market has increased rapidly to around 40 billion won market. And office space and shopping patterns change has had impact on the real estate market. In the United States, after the outbreak, the commercial office space in 10 major cities of the United States, you can see the vacancy rate is going up. Same pattern is found in Korea as well. But the only difference here is that in the case of Korea, the urban center is showing different pattern from Gangnam area. In the traditional commercial business district, the vacancy rate is going up. However, in Gangnam area, ICT and digital related on-demand industry has grown rapidly, and these new industries are replacing taking digital office space. So the vacancy rate in Gangnam has not gone down drastically. Commercial business district at the bottom, by size. Medium and small sized offices are showing high rate of vacancy, but mid to large office space, because of various reasons that I've mentioned earlier, have not been hit hard. And leisure space. Regarding leisure space of London, after the shutdown and lockdown measures were introduced, recreation space like parks were closed to the public. But in spite of such restriction, in terms of overall usage of leisure space, park and recreational space around residential area has seen an increase in demand. Because of the mobility restriction, people were becoming more active around their neighborhood. Same thing happened in New York. More than 10% increase has been observed in activities around neighborhood green areas. Same thing is happening in Japan. When it comes to neighborhood parks, they are seeing increase in use. And Seoul is also showing very strong pattern. Relatively speaking, in Korea, we have been relatively free from the impact of shutdown. The overall activity level has not gone down greatly. And when it comes to mass transportation, retail, overall volume has declined a little bit, but the certain level of activities have been maintained, and there has been explosive growth in the demand for park areas. So after the COVID outbreak, because of the social distancing, we could not use restaurants or cafes like before. And the demand for leisure space in Korea has gone up more drastically in Seoul than any other cities. When we look at transportation and mobility, floating population, public transport has been hit hard, but walking and self-driving, even though overall level has gone down, compared to other cities, Seoul has maintained relatively high level. And in the third surge, the overall transportation has not gone down in terms of volume. After the third surge in pandemic. I heard in the news today that we are now seeing the number of infected rise up to 3,000 level, and changes in floating population has not been so drastic compared to the first and second wave. Of course, we have to pay close attention to the future changes. So when it comes to changes in leisure space pattern, GIS, we have seen drastic rise in activities around Han River area and urban green area. And also in Seoul, there are areas that have difficult access to leisure space. And the citizens in those areas are complaining about lack of green space to the government authorities. So let me talk about the fact that there will be a rise in the demand for people to use community space. So in summary, the world trend and Seoul trend are going in more or less the same direction. There were a lot of similarities and some differences as well. Such overall trend in change in residential, office, and leisure, the changes in those spaces are demanded. And in the case of Korea, we need clear and bigger changes in such spaces. And this is going to lead to a new urban model. And we are currently thinking about such changes in urban mobility pattern. And they are widening and decentralized, and strong hubs based on public transportation will be restructured. And living SOC, such as recreation and green leisure space, in line with the office change, the demand will go up. And also, when new mode of transportation is developed, I'm sure such demand will only increase. So mobility or land use change, housing price changes, through big data, we can monitor them real time. And how this is going to be reflected in urban administration is something we should do further research on through various channels. It's one of our future tasks, and mega city region could be built around the entire nation, and such demand will be accelerated because of COVID-19. And according to 2040 Seoul plan, we are designing a 15-minute community-based city, and close distance demand will become more important, and we will see more and smaller spaces being built around the neighborhood as a part of a new urban model. Like, New Seoul is a combination of 100 small cities. Around this new living zone, we will see integration of living, work, and leisure as part of new urban hub, and green transportation like bicycles and urban space restructuring and activities will be enhanced. And cities in the future will be community-based land use pattern-based urban planning. And such changes we have to continue to think about how to overcome such changes. Thank you very much for your attention. Thank you very much, Professor Lee. It was a wonderful presentation. New York, Tokyo, London, Seoul. You have shown us the data comparing those cities, and you have said that the COVID-19 outbreak's impact on real estate market is that overall real estate prices have gone up. But in terms of space, there's decentralization. But in some areas, there is an increasing level of concentration. COVID-19 has made us vulnerable to infection. So people did not want to use public transportation, meaning that people are living close to their work or working close to their residential area, or they are leaving the downtown area altogether. So the demand for housing in outer skirts of urban areas is going up. And centralization and decentralization is going to be the theme word for development model. And megacity zone will be required to create a wider area, but people want to live close to work, so there will be a lot of fragmentation in the city area. So he has shared with us his future research direction. It was a wonderful presentation. Next presentation is going to be made by Professor Park Inkyu of Physics Department. He will talk about global urban digital model and toy modeling of COVID-19 spread, how a city perceives the urban environment. Professor Park?
네, 안녕하십니까.
Hello everyone. I cannot see my first page of slide. Yes, and now I see it. The title of my presentation is actually a global urban digital model, which is a new concept, and I'd like to introduce this new concept. I'm not standing here to show you the research result or explaining the research result. Rather, I'd like to share with you that our research after COVID-19 is definitely what we need. So it's actually giving you a proposal, not only my university that I work for, University of Seoul, but also there is Seoul Institute of Technology and Seoul Digital Foundation, Seoul Institute. Every single party, they must be interested in this research. So my presentation purpose is actually giving you a proposal. I don't know how I can. Okay, fine, thank you. Now I see my slide. So, first of all, what is global urban digital model? I created this concept. And second, toy modeling of COVID-19 spread means, so within a city, how COVID-19 virus is spreading. So it's not applying to every single cities, but rather in a toy modeling way, we try to understand this. I'm going to talk about three things. First is global urban digital model, what it is and how we can apply this. And secondly, how physics can we understand this city, how can we work together with the cities, what kind of tools in the physics studies can be utilized in the urban studies. And I'd like to give you an example of a very small model and try to understand how the toy COVID-19 spread model works. The reason why I'm going to talk about the three things is probably you might remember in 2020, as the new year started, COVID-19, it shows a peak. About 500 people got infected because of this cult religious group, and then there was a peak of 2,000. And since last week, the confirmed cases once again recorded like 3,000 to 4,000. And the physicists or mathematicians can never predict such a peak. Whenever such a peak happens, the government and quarantine authority intervene, and they try to come up with new quarantine policies to reduce it. And the system cannot be predicted by the physics nor mathematics because there is a human intervention. That's why I believe the GUDM and COVID-19 model is very important. You might remember the Nobel Prize laureate. The three people received Nobel Prize this year. One is a Japanese, and Klaus Hessmann and Sukuro Manabe and Giorgio Parisi. So as you can see here, two people studied particle physics. The other one, complexity physics, was his major specialty. So what is complexity physics? Why did they receive Nobel Prize? In a nutshell, this is the model they have created. Actually, this picture was taken from JUICE 5 physical model of Earth. They have the simulator. What they're doing is they try to measure carbon dioxide and how the carbon dioxide is flowing and spreading following the Earth's atmosphere. We call this as a physical model. How this is possible? Well, because we are not just applying the complexity model, but we have this grandiose computation power that we applied. So all the data existing in the world can be input, and the physics parameters can also be inserted, and afterward we can understand how it is moving. So based on this, we can prove the global warming, and this year they actually received Nobel Prize. What do you call this? We call this, I'll call again, but global urban model. So let me tell you briefly about the complex physics system. As I mentioned before, complex system means a system composed of many components that interact with each other. So there could be examples of the power grid, network infrastructure, Earth's global climate, and even inside the urban city, all kinds of transportations, and how the money is being transacted, how the virus is spreading around. This is so-called fall under the category of the complex system. We cannot just understand this by studying one, but all kinds of interdisciplinary activity must be done. Of course, the statistic should be the backbone, and we have this nonlinear dynamics, and also information theory needs to be included. Definitely computer science must be included so that we can do the simulation. Not only that, but also we need as a content sociology, economics, psychology, all kinds of the studies must be aggregated so that we can understand the complex system. My university of Seoul, we have launched Big Data Research Institute, AI Research Institute, and now we have invited expert in the urban study. So Professor used to study in UK and now joined the University of Seoul to study the complex system. The moment that he joined, he is trying to conduct research on the urban cities utilizing the complex physics systems. So all data happening in the urban area, how urban physics like complex systems can be connected. So Professor is writing a thesis, Seeing the Cities Through Big Data and Complex System. Probably you might have seen this. The Seoul digital twin has been announced. What do I mean by this? It means that the size of the Seoul, which is about 600 square kilometer and about 25,000 aerial photos have been used, and around 600,000 buildings are included. And using this, Seoul Metropolitan City government is trying to come up with a 3D map. For example, driving urban wind path, they can prevent fire spread, or they can localize urban heat island, or 3D virtual tour can happen so that the foreigners, they don't have to come and visit Seoul, but actually they can see what Seoul looks like, or time machine trip to Hanyang or the capital of Joseon Dynasty is also possible. What you're looking at right now is a 3D map, and at the center is the Seoul City government building where our meeting is now being held. So every buildings are included here. This is a big thing. Based on this model, we can do many things together. Now, I'll give one example. Here in this model, we can include how the wind passes by. So between the buildings, how the wind path is flowing, and by analyzing the urban wind path, we can understand everything. So this is actually going beyond 3D map, going toward the spatial analysis. Now, here I'd like to give you definitions of the global urban digital model. Why am I doing this? Because we have the GCM or GDAPS, which received the Nobel Prize this year. So this GCM or GDPS, they are based on all kinematical and dynamical variables and measurement big data in the Earth's atmosphere. And only when they encompasses big data, we can understand that. So if we get rid of the Earth, then we can call this as global Earth digital model, or we can get rid of the Earth and then put urban, so global urban digital model, which means that not only the mountains or buildings, roads, traffic systems, power lines, water pipes. So what I mean by that is not only the mountains, rivers, atmosphere, or geography, the nature built by God, but also the buildings, roads, traffic system, power lines, and water pipes network built by human being, and also the population, transportation, energy consumes, the dynamics, all of these can be included here. Then how physics can help us understand the cities. Let me briefly touch upon the particle physics. Probably you might remember this. In 2013, Nobel Prize in Physics were given to the François and Englert and Peter Higgins. Let me explain how they have received the award. Well, probably you might have seen from the TV how they did it. So the two particle clashes in creating a fireball, and then all kinds of the particles came into being, and the physicist says that this is a very special Higgs particles. But how can we be so sure that these are the Higgs particles? Let me tell you what they are doing. This is what they are doing. So these are the number of the things they do. First, 10 trillion is spent to build this collider, and then we create this detector, and detector is very critical. So this photo is quite small. I will show you a bigger one later on. So we get the big data from the detector, and then using computer, we analyze, and then we distribute that to universities and academia around the world and try to understand the Higgs particle. So if you look at the detector in a closer thing, you see that one of our graduate school students are trying to understand this using detector. So hundreds of millions of signal lines are included there, and detectors are the aggregate of these sensors. They create signs, and the data are created. About 18 tetrabytes are created. So the size is like 100 times or tens of 1,000 times bigger than what we have collected. So all of these data can be analyzed by computer. So when there's a collide, what happens? This is what happens. So this is the moving image. So two beams clashes, and the particles are created, and hundreds of these are came into being, and the final collide image are being created. So what do I mean by this? So there are tools used by the physicist. What they are, I believe that this is for the first time, digital twin can be completed, because within the collider, all kinds of phenomena, all signals, all geometrics are included here. And then finally, the physical result can also be seen. And why can, even if we can represent this, why do we have to look at this? Well, the Gen 4 is the standard tool for the virtual particle experiment. It describes the interactions between the particles and matter. So starting from the medical healthcare to all the way to the universe, this digital twin is now being applied, and this is not that difficult. Most representative case is that, as you can see here, one collide was represented, replayed again. If we analyze it, you can see these kind of reactions. Let me explain how this works. It might look quite complicated, but the black dot means the data that we got by testing, and if you see the red line, straight line, that means the line that we got from this, and the black and red are quite similar. But those that are not red, it doesn't fit well. So-called the real experience, not the digital twin, we got the numbers and we can tell that these are the Higgs particles. So what I'm trying to say is that digital twins are already being used. It's existing legacy technology, and we need to apply to the city as soon as possible. So let me quickly touch upon the remaining slides. Then, TOI GUDM, how can we implement that? And also COVID-19 spread. We can definitely require a huge amounts of the computational power. Of course, we cannot do this inside a small lab, but rather using our idea, we can create a really small TOI GUDM. Because TOI GUDM does not require a huge amount of the investment, and we can understand how they have made impact to the outside. Because when the policymakers would like to see that when we upgrade to the first stage, to the second grade, or to the third stage, what might happen, and whether their policies must change or not. So as a TOI model, we will measure that. This is the most representative one, as I mentioned before. This shows the lessons from the COVID-19 statistics. And every time when the peak happens, the human being intervene. And to what extent shall we intervene so that the confirmed cases can decrease? How can we know that? We can understand the reality. So let me show you the simulations. What you are looking at right now is the 80 meter to 80 meter, which is the campus of the church or campus of the, once again, the schools. And whether they could dance or whether they could or have fun on whatever they are doing, we can do the simulation. So for your reference, the yellow color ones are the ones who are not wearing mask, and those who are wearing a mask are the ones who were confirmed in the beginning. As you can see here, so they are moving around. Of course, they are not wearing mask. So definitely the spread is being carried out very, very rapidly. And the moment they spend there are very different than the time that is in we spend in the real world. So as time goes by, they turn into blue color, which means that they are being cured. And then of course there's about 5% of the fatal rate. And here there are people who die without being cured. So let's go quickly. You will see that the 20 people, they don't wear a mask, and then they wander around, and then eventually 14 out of 200 dies. Now let's switch the model a little bit, and then we will look at if the 50% wear mask, 50% don't wear mask, and then even you can see that the yellows are those who don't wear mask. Same thing, the spread happens all the way up to 50% and all the way up to 100%. And until the last moment, you can see that out of 210 will be the victim. So it's not decreased much. So when the 50% wear mask, it's not that meaningful. Now, lastly, very dramatic one. If 90% wear mask and 10% take off their mask, what happens? Let's see. As you can see, the spread happens, the virus, because 1 out of 10, it happens, but self-healing can happen, which means that in a nutshell, there are no victims at all. So what I mean by that is that COVID-19 is quite scary virus, but Korea did fairly well, while the United States, they suffered from 400 to 500,000 people passed away. But in case of Korea, they didn't die because we were strictly complying with the mask, and we can see that proof during the and also we can apply to the moving data. And what do I mean by moving data? 2013, it's a taxi data that we got, and Seoul Traffic Information Center, and together with the Topis and T-Money, they gave me the information. So we found out the locations of 10 taxis, the speed, the directions, and also whether there are passengers riding the car or not. So we analyzed the data. We came up with the idea that during the morning and night, the amount and the number of the passengers, the amount of the payment have increased drastically. But as you can see here, the blue line, the speed is really quick, but there are greater number. So we can actually use 3D map, and you can tell how condensed they are. And from there, we go one step down the road. As you can see here, it's the University of Seoul, and you see that a lot of people have gathered around University of Seoul, and you know how they are moving around. So using this data and also the toy model, if you apply, how can we come up with the result? And I will share with you the result, and I will end my presentation. On the left, you will see this toy city model, and from the moving data, they have extracted 2,000 groups, and this 2,000 groups goes around and around. Whenever they move around, we see that very small scale or micro scale of the contact happens, like 0.5% of the contact has happened. In the early model, Yeouido there's 1 and Cuauhtemoc 1. So around 4 to 5 were infected in the beginning stage. And here, urban mobility data, how can we apply this all the way to the Seoul Metropolitan city? Very rapidly, they decide to come to all the way to Jongno. And if we don't wear mask, and if the COVID-19 virus, we got infected, and then using this model, we found out what might happen. We can come up with a prediction, and the quarantine authority will be able to enjoy the great result. Let me give you the final conclusion. First, the urban phenomenology, the various urban dynamics are all complex systems. So a complex system is something that you cannot ignore, because what happens in the city, not only the data is complicated, but also the data amount is huge. So the phenomena that happens within the universe probably might be much higher, but because because it is intervened, it decreases. In order to understand what is happening in urban, especially in the complex system, we must have the urban physics. Then, in order to do the urban physics, what kind of tool do we need? The biggest tool is a digital tool, because urban physics is to understand the dynamics, and to understand the dynamics means that we need a model, and we need a digital twin to simulate this. So 3D map is not same as a digital twin. Please understand that. However, the kinematic, and also other values are included within this, and the big data are all big data must reside so that they can analyze that. And are they only for the purpose of the productions, or what they are doing? Well, the digital trend is already using it. And lastly, we can use that. Digital twin can become a major tool for understanding the urban physics. We need digital twin with the kinematics and dynamics variable, as well as measurement in big data. And the particle physics has shown already examples of the real digital twin, and we can make a global urban digital model. And toy GUDM is very easy to make, and toy GUDM shows a promising output in COVID-19 spreading model. You have to understand that the toy GUDM is only a toy model, and starting from today, maybe you can all come up with a GUD, and all these all metropolitan cities and the relevant organizations can help together.
역시
Professor Park. It was a very interesting presentation, especially complexity system, the planet level.
And he just changed into GUDM and tried to do the simulations during the COVID-19 era, especially the Seoul Metropolitan City implement digital twin model, and also the taxi model is being operated by Seoul Metropolitan City. SER is a COVID confirmed route, and kinematic or kinetic approach are all mingled together and have been used. And I believe that every year the Big Data Forum will be held, and I hope we can have a further discussions and collaboration in this field. So far, Seoul, University of Seoul made a presentation. We have 2 more presentations to go. And let me invite the first speaker. First speaker.
He is Dr. Cuauhtemoc Anda. He is from Mexico, and he is now working in Singapore in a company called Data Spark. He has received his doctorate degree in ETH University of Singapore, and then he has been making presentations at Seoul Big Data Forum from the very beginning. He will talk about latest research and development efforts on the topic of mobile phone data and transportation. So he will talk about how to get the mobile phone signal to get the useful data that we need in order to prevent the spread of the virus and for many other use. Dr. Anda, please start your presentation.
Good afternoon, everyone. First of all, many thanks for the invitation to the Seoul Big Data Forum this year. I'm very excited to share with you on our latest research and development efforts, particularly about enriching mobile phone data from process to COVID-19 use cases. My name is Cuauhtemoc Anda, but you can call me Temo, and I'm a senior data scientist at Data Spark in Singapore. This presentation is divided into 3 different parts. In the first section, we are going to define what exactly is mobile phone signaling data. Then, in the second section, I'm gonna show the latest research and development project we have at Data Spark, which is called the Trajectory Enrichment Project. And finally, for the last part, I'll show a couple of mobile phone data use cases related to COVID-19, one for Singapore and the other one for Australia. So what is mobile phone signaling data? The way the mobile network operates is that it needs to be in constant communication with your mobile device. So imagine there's a person carrying a mobile device at location A. Her mobile device will connect to the closest available cell antenna, and it will leave a record consisting, among other things, of the timestamp and the mobile ID. When the person decides to move from location A to location B, her mobile device will connect to available cell antennas that are along her trajectory, leaving the same type of record. And when the person reaches her destination at point B, the same type of communication is going to get triggered from the closest available cell antenna. The longer the person stays at location B, the more communication events are triggered and the more data collected by that particular cell antenna. So why is mobile phone signaling data useful? So as we could see, it gives us an approximation of people's location and movement. One of the big advantages of mobile phone data is its extensive coverage, meaning that you get population-wide samples, where this is directly related to the market share captured by specific telecommunications provider. It is longitudinal data, meaning that the data is collected 24/7 for every day of the year. In principle, there's not much more investment required, since this data is already being collected for the purpose of serving mobile devices in the network. That means that if you want to use it for different purpose, like transport planning, then this type of data can be categorized as opportunistically collected. And in the transport research community, we have been very excited about this because mobile phone data allows us to understand travel demand in ways that it was not possible before. Here is a real example using my own mobile phone data. This happened at the beginning of last month, on the 7th of October. The red markers are the different cell tower locations, and the number in those red markers indicates the number of connections my mobile device had with that particular cell tower. If you inspect closely, you'll see that there are some areas where the cell towers have many more connections. These areas are directly related to places where I was doing an activity. First, location A is being my home location. Then, after spending some time there, I left and met a friend. We went bowling at location B. After bowling, we went to grab dinner at location C. And then finally, I came back home at location A. If you connect the dots between the different locations, you'll start getting some information and some sense on how those trips happen. But as you can see, the spatial temporal resolution of those trips is not as good as what you would expect, for example, from GPS data. Here is the same data, but in a 3D plot, where the z-axis corresponds to time. Here you can easily identify the different 3 locations, and you can also have a sense about the time I spent on each of them. However, when we turn this 3D plot, you'll realize that things are not that easy. There are actually several oscillation effects happening along the trajectories. These oscillations are a natural phenomenon derived of how the mobile network operates. However, if you want to use this data to describe people's movement, then you need to be very careful, because in those situations, the person might not be moving at all, yet you'll see jumping signals on the data. So what are other challenges when working with mobile phone signaling data? First, we saw that the spatial resolution is not as good as GPS. It is actually given by the density of cell antennas deployed in a city. The temporal resolution changes, and it's given by different factors. Some of them are factors related to the user, some others to the mobile device, and other factors related to how the network operates. As we saw, we have the problem of the tower oscillations, which is something that is part of how the network operates. If you compare this type of data with, for example, the household travel survey, then you'll see that here you don't have any type of contextual information. You don't know what are the trip purposes. You don't know what was the mode of transport. You don't know what were the different activities the people were engaged with. And this is because, of course, this is an opportunistically collected data. So it was originally not designed to do mobility analysis in first place. So the current situation now, the reality is that without any further processing, raw data can only give you a very rough estimate of people's count at a very low spatial resolutions. However, we can do better. It is possible to a certain extent to infer, for example, on what was the transport mode, what was the particularly route taken, to map match to specific transport network links, obtain, for example, travel times, improve on the spatial temporal resolution, and extrapolate to population-wide statistics. But in order to do this, we need first to have a very good understanding of how mobile phone signaling data behaves. We need to exploit the large historical and cross-sectional data sets, and in order to do that, we need to harness state-of-the-art inference models or even develop them, where these inference models can be, for example, deep learning ones or even probabilistic. So this is part of what we do in DataSpark. We design and deploy algorithms and pipelines to create mobility building blocks from raw data. Those mobility building blocks then allows us to make mobile phone data more useful in many more applications for different sectors. One example of our research and development efforts is the Trajectory Enrichment Project. To introduce the problem, let's take a look at a trip from a popular shopping center in Singapore, the Mustafa Center, to the Changi Airport. This trip was done by a car and using the Pan Island Expressway or PIE. And what we see here is how the particular trip looks in the mobile phone data. So let's assume that the same person does the same trip again, using the same car, taking the same route, and at similar times. This is how the second trip might look like. As you can see, there seems to be data gaps in different parts of the trajectory. Now let's assume that the person does again the same trip. This is how it would look like. So a very sparse trajectory. So the situation that we have is that the quality of trips that are extracted from mobile phone data varies a lot. So the objective of the trajectory enrichment project is to improve on the completeness of these trips, especially the sparse ones, given that you have a large historical data of similar trips. To solve this problem, we designed the cluster Markov model for trajectory enrichment. For the cluster Markov model, we start by extracting a collection of trip trajectories from same origin destination, where the resolution of that origin destination can be given, for example, by the smallest planning area in a city. Then the cluster Markov model has 4 different steps. In step number 1, we want to find clusters of similarity from that collection of trip trajectories. Then, in step number 2, we train a Markov model for each of the clusters obtained in step 1. Given a new observation, so this is a new trip, in step 3, we assign that trip to one of the predefined clusters. Then finally, in step number 4, we use the cluster Markov model of that cluster to enrich the trip trajectory of the new trip. For step 1, finding clusters of similar trajectory, we chose HDBScan as our clustering algorithm. HDBScan is a hierarchical version of DBScan, which allows us to obtain clusters in regions where the densities differ. But more importantly, either you choose HDBScan or any other clustering algorithm, you need to represent the trips as a fixed length feature vector. Hence, we cannot use the location updates on each trip directly as a feature vector. Each trip has different length. So our solution for this was to compute what we call characteristic points of the trip. Those characteristic points divide the trip trajectory into k equidistant points. So in this way, every trip will have the same number of k equidistant points. Then with these points, we construct our feature vector composed of the location of those characteristic points, the delta times in consecutive points, the angles created, and the speed. After obtaining the clusters, then step number 2 trains a Markov model for each of these, for each of the clusters. The key idea here is that we define the Markov states as the locations of the cell antennas, and the Markov process is the transition from cell antenna to cell antenna. There are 2 classes of parameters that need to be learned. The first one is the transition matrix, and the second one is an initial state probability. This can be done very straightforward if we use maximum likelihood estimation, because learning those parameters directly translates to counting the frequencies of events in the training data. In step number 3, we want to assign a cluster to a new observation, to a new trip. To do that, we leverage on the Markov model being a generative model. So we compute the probability of a cluster that a cluster has of generating that particular new trip. That probability is constructed using the parameters of the Markov model. So one part of those probabilities is related to the state initial probabilities, and the other one is composed by the state transitions probabilities. The cluster that is assigned in the cluster that is assigned is the one that yields the highest probability of being able to generate that new trip that we have. And here we have to remember that the new trip it can be a very sparse trip, right? Because that's the objective of what we want to achieve here. Finally, for step number 4, we want to enrich that sparse strip given the Markov model of the cluster assigned. Here is an example of how we can do that. So let's assume we have a trip T, and trip T has a series of location updates, x0, x1, x2, and so on. So let's focus on the first two, x0 and x1. So we ask the following question. Is there any missing data between location updates x0 and x1? To answer that question, we test a different number of hypotheses. The null hypothesis is that in order to arrive to x1, we are actually coming from x0. And then we calculate the probability of that, of how probable is that to happen. For the next hypothesis, hypothesis 1, we use the Markov model to generate the most probable location coming from x0. And we assign that as x0 prime. Then hypothesis 1 tells us that in order to arrive to x1, we are actually coming from x0 prime. And then we calculate the probability of that transition. Then we continue with hypothesis 2, and in similar way, we use the Markov model to generate what's the most probable next step given the latest information we have. The latest point we have is, in this case, x0 prime. So then we generate what's going to be the next most probable location, and that location we assign to be x0 double prime. So hypothesis 2 tells us that in order to arrive to x1, you are actually coming from x0 double prime. So this is how we can continue doing these different hypothesis tests, and we do it for a fixed number of tests. Then we choose the hypothesis that yields the highest probability and insert the corresponding series that were generated of location updates in between x0 and x1. So for example, if the highest probability comes from the null hypothesis, then that means that between x0 and x1 there was no missing data, so we don't need to do anything more. But if the highest probability comes from hypothesis 1, then in between x0 and x1 we insert that the location updates that were generated. In this case, this is x0 prime. If the case was that hypothesis 2 was the one with the highest probability, then that would mean that in between x0 and x1 we'll have to insert x0 prime and x0 double prime. So we have to repeat this same process for every pair of consecutive location updates in the original trip. So now that we have the cluster Markov model, how can we test whether this approach is effective? We already have our dataset of trip trajectories, and then the next step is that we need to filter those trips that show very good spatiotemporal resolution. We then split the dataset into training and test splits. Then from the trips in the test data, we randomly drop out some of the location updates. Those artificially generated sparse test trips are then used as an input to the cluster Markov model. And then we validate if the cluster Markov model can recover those deleted location updates. So let's see an example. Let's use again the same setting, trips coming from Mustafa Center to Changi Airport. Here I'm showing 4 of the most popular ways to do the trip. The 2 above are car trips using different expressways. The one on the left is the PIE or the Pine Island Expressway. The one on the right is the ECP or East Coast Parkway. Then the two different ways to go on the bottom. The one on the left is using the downtown line from the metro system, and the one on the right side is also the metro system, but or MRT in Singapore, but is using the east-west line. So for the first step, when we do the clustering, what we obtain is different clusters that actually that directly relate to these different and popular ways to go from Mustafa Center to Changi Airport, as we can see here. Then we continue by learning a Markov model on each of these clusters that we found. The next step is to look at a new trip. Here is the target trip. It is a trip being done by a car and using the ECP, the East Coast Parkway. Then, given this information, we create what's going to be the input for the Markov model, where we randomly drop out some of the locations, as you can see here. So there's two, for example, in this case, there are like two gaps created along the trajectory. And then we input this trip into the Markov model and see if we can recover what we had as the target trip. This is the result of the cluster Markov model. And as you can observe, those location updates that were deleted were actually recovered by the model. And even more, the spatial resolution even looks better than the original target. Here is a second example using a different expressway, the PIE. We can see here the original trip. And then the same process, we drop out randomly some of these location updates. In this case, this example is a more challenging one. As you can see, there is a big portion of the trip removed. Then we use this input trip to the cluster Markov model. And then we can see that the cluster Markov model is capable, even under this situation, to recover the missing, the deleted locations. So the importance of doing the trajectory enrichment project is that it allows us to map trajectories into specific transport links more efficiently and also with better accuracy. It also helps us to infer what can be the mode of transport that was used. Then, if we are able to do this, then we can validate, for example, traffic counts with external data sources. And that's something we did in Melbourne with VicRoads data. VicRoads is the transport agency for the state of Victoria. And as observed here, there is a very good match between the traffic counts that we estimate against the traffic counts captured by VicRoads. Here we zoom in into a specific area in Melbourne, the Flemington Racecourse. And as we can observe here, the counts that we get from our pipeline come very close to those counts that are captured by VicRoads. For the last part of the presentation, I'll show two different COVID-19 related use cases. And both of these cases, they are built on top of our processed mobile phone datasets. The first one is a case in Australia, where DataSpark collaborated with Queensland Health, which is the public health department of the state of Queensland in Australia. We developed and provided an epidemiology tool to assist Queensland Health in their current challenges amid the COVID-19 pandemic. With that epidemiology tool, the analytics team in Queensland Health are able to understand where people who had been exposed to a high-risk COVID-19 area had traveled to afterwards and where do they normally reside. Queensland Health has converted these insights of the DataSpark epidemiology tool into different actionable items. For example, they are able to make informed decisions about where to establish pop-up clinics. They can also include different suburbs in the COVID-19 alert list, given the information they can see in in the epidemiology tool, and they can even further develop predictive models to determine the spread of COVID-19 in the community. Here we can see a small animation which is part of the DataSpark's epidemiology tool, and in this animation we can track the evolution of locations visited by people who went to COVID-19 exposure sites. So the greener and darker the area, the more people who was exposed to a high risk area has visited that area. This corresponds to the beginning of the outbreak just recently in Sydney in July of this year. And one of the interesting things is that while we were tracking the day-to-day evolution of the outbreak in Sydney, we could actually identify first the areas that the government would later announce as high-risk areas using exactly this methodology. Finally, for the use case in Singapore, we have released a report covering the evolution of COVID-19. By the way, this report and also there's a report on the previous use case on Queensland Health. Both of them, they can be found on our website and downloaded. From the Singapore report, I chose one of the figures where we can see in blue the relative number of daily workers that travel to Singapore Central Business District from February 2020 to April 2021. We can observe how the evolution of COVID-19 has impacted the change in the number of workers traveling to the CBD. And if we overlay the relative daily new COVID-19 cases, those ones are here in pink, then we can start making some interesting observations. First of all, we can see that as soon as the number of cases started rising in the first wave, Singapore decided to do a hard lockdown called the circuit breaker. This allowed, as we can see here, people stop abruptly coming to the CBD Central Business District area, and then we can also track here how those daily COVID-19 cases started dropping. As the cases started dropping, Singapore started slowly reopening again, and we could track this in the blue plot again because the number of people traveling to the CBD started increasing back to normal slowly. So what are the takeaways of this presentation? First, mobile phone signaling data can be very useful for many applications in different domains, but different technical challenges need to be overcome. There's very little value that can be extracted from the raw data. In order to exploit mobile phone data and meet the expectations, we require proper data pipelines and AI algorithms. One example is the trajectory enrichment project, where the data quality of trips is substantially improved. Finally, in the past couple of years, we have experienced how mobile phone data has become a valuable asset amid the pandemic, because it can help to anticipate epidemic outbreaks. It enables faster reaction from organizations with informed decisions. It can be used to evaluate the spread mitigation strategies in different cities, and it can also help to quantify the economical impact in different sectors. This is the end of my presentation. Thank you, and I'll be glad to answer questions and comments in the discussion session.
굉장히 발표를 잘 하셨습니다.
Thank you very much for your presentation, Dr. Anda. And mobile phone signal data can be used to estimate the trajectory of that person in terms of space and time throughout the cities like Queensland and Singapore. He has offered 2 case studies, and along with, if you can combine that with the census data using Markov chain model, so starting from your home, and it can identify trajectory of where you have gone, and through that trajectory analysis, you will encounter many other people, and through encounter analysis, you will know who have been contacted and use that for SCIR or epidemiological purposes. So, you can simulate that kind of information to identify how the infection can spread. And Data Spark is a very big company, IT company, and they have used the raw data for all this kind of analysis. This is really useful, in my opinion. And in this with COVID-19 era, I hope we can improve the safety of our society using this kind of information
우리가 위드 코로나에서도 조금 안전하게
so that we can stay safer in this with COVID era. So any further details, we can come back to them during the discussion session. The last presentation is going to be made by two gentlemen, and it's titled Learning Urban Mobility and Activity Patterns with Kyoto Case Study During and After COVID-19. So Professor Jan-Dirk Schmoecker, professor of Kyoto University, and then he has received his doctorate in Imperial College London, and he is now has moved to Kyoto and became a full professor and a postdoc researcher, Wenzhe from Kyoto University. He is also going to make presentation. So we'll listen to the presentation by these two gentlemen.
Good afternoon from Kyoto, Japan. My name is Jan-Dirk Schmoecker, and I'm giving this presentation together with my colleague Wenzhe. The title of our presentation is Learning Urban Mobility and Activity Patterns with Kyoto Case Study During and After COVID-19. I will give a general introduction to this research, including the wider context and the project of which the specific study, which will be presented by my colleague Wenzhe, is part of. After the presentation of our specific study, I will return for some general conclusions. I start my presentation with a slide that we are all too familiar with. These are COVID trends here observed for Germany and Japan, two countries I'm close with. In both countries, we can see different curves, and some of these aspects of these curves are well explainable. They are resulting from different policy measures. We have lockdowns, we have restrictions in shop opening times. We had them in both countries, and these lead to these, and then these restrictions were lifted at a time when we thought that the COVID cases are under control again. These lead to these curves that we are all familiar with. I will also emphasize the huge difference in COVID cases in the last days. In Germany, it's largely rising. In Japan, it keeps very low even after restrictions have been removed. And explaining this and some other aspects of these curves is not easy. There are a range of policy measures that I try to group here into containing measures and also in terms of recovery measures. Containing measures are travel and activity restrictions such as lockdown. Then there's a range of social distance measures in transport as well as else in our daily life, as well as, of course, vaccinations. These are all measures to contain the virus. Then on the other side, there are also measures, and these measures arguably will become more in the next months, years, when we hopefully come to end of this crisis that try to encourage people to travel more. In Japan, there has been the Go to Travel campaign, a measure to stimulate the economy at the time, to recover from COVID at a time when the COVID cases were low. So this campaign was providing people with subsidies, providing travelers with subsidies if they travel to a different province and stay in a hotel. So part of the hotel fees were reimbursed. And there were different waves of this Go-To campaign, but so it was stopped when the cases were increasing again, and then it was relaunched. But it did stimulate, as we will show in our study, it did stimulate some travel. The resulting research questions for us are, well, we have these different range of policies, we have COVID cases, and then we have mobility, and we want to understand the role of mobility patterns. Mobility patterns here having a very central role in the COVID cases, in explaining COVID cases. But also, our focus is on the mobility patterns itself here. And I should also mention there's a dual role between mobility patterns and COVID cases. Once COVID cases are increasing, even without policy impacts, people will not feel comfortable to travel and therefore reduce their travel. Then there is a large other aspect here. There are clearly a huge number of other factors that influence mobility patterns and that influence COVID cases beyond those three groups of policies. There are seasonal factors. Then there is something we might call COVID fatigue. So we understand that different COVID policies have different impacts at a different effectiveness at different times during the crisis. So for a researcher, what we want to estimate is the parameters associated with these arrows that I draw here. Further, to understand better these interactions between these different arrows. Thirdly, there must be time lags in that, especially some of the fears and some of the recovery measures will take a time until they turn into changes in mobility patterns. And of course, we try to minimize this effect of, we try to really extract the knowledge of the impact of these policy measures, i.e. to roll the minimize of others. Talking about mobility patterns, we suggest it's useful to distinguish here between enforced measures and unenforced measures. Enforced measures are kind of obvious, such as lockdowns, such as restrictions, whereas unenforced measures are something like panic buying. Well, and here you see a picture of a lady buying a huge amount of toilet paper. In the beginning of the COVID crisis, there was a fear in Japan, it was unfounded, that toilet paper would become scarce. So this was not an enforced reaction of people, but suddenly a trend appeared for people to purchase this product, and a trend that was reinforcing itself. Then there are changes in activity and in destinations, changes in mode choice, and also to emphasize is that these restrictive measures we can enforce, but recovery methods, of course, we cannot force people to travel. So these can also only be unenforced changes in travel. Furthermore, what is important is to distinguish rapid changes from gradual changes. And enforced changes are often gradual, but not always. And hopefully they're non-permanent, whereas unenforced changes are more likely to lead to longer term and to more permanent changes. Some of those, not all. The resulting research questions are, how can we distinguish different policy impacts on mobility? What are appropriate models to actually forecast changes in travel patterns? What big data are useful for such predictions of policy impacts? And how to fuse data and distinguish causalities from correlations? And I mentioned on the previous slide the dual relationship between mobility patterns and COVID cases. More generally, we might say, well, what are the results? How can we design our cities to become resilient against COVID and similar crises? What long-term policies in terms of infrastructure investments are needed, and what short-term policies are needed? These are again those different policies measures that I grouped in the previous slides. This will relate to activities, and this will then relate to resilience targets. And actually, it's also, we suggest, a question in itself, how we define a city to be resilient. I want to conclude this first part by mentioning the overall project that of which the specific that we're going to talk about soon is part of, and that's the DALUMA project. The acronym stands for Deep Learning Anticipated Urban Mobility Peaks. So the idea is really, can we predict some of those changes that we have observed? And can we use a large range of different data for it in order for our cities to become resilient? I think this DALUMA is a nice symbol for it. It's a symbol of resilience. It's a figure that can fall but will always get up again. And we hope that we can design our cities in such a way that they also get up again at every time. And with that, I want to pass on to my colleague to talk about the specifics of our project.
Thank you, Jan-Dirk. In this fight against COVID, we have noticed several open data sets that can provide general trends of human mobility and activity. The audience might have been very familiar with the curves drawn by Google Mobility Reports. These activity trends are based on the use of Google Maps and are divided into 6 categories: retail, grocery, park, transit station, workplace, and residential. The data are processed as a percentage change from a baseline in January 2020. In addition, Apple also provides a mobility index for car, transit, and walking based on their map services. These 2 data sets are available at city level and for each day. However, it's not enough if we want to know the demand dynamics of a specific place in a specific day. To learn these high-resolution demand trends, we use Wi-Fi packet sensor. We have done some experiments in Kyoto City for several years, including an experiment in our campus since this year. The sensor receives every probe request sent by smartphone for Wi-Fi access in every second, so that we can capture within-day dynamics for a place. A new problem is therefore it's not practical for a city to install sensors for each shop, restaurant, and etc. Here we introduce a new data, Google Public Times, the GPT data. It provides historical and real-time business for a number of places throughout the city. If you use Google Maps, you should have noticed the red bar, which is the live GPT data. We have around 2,000 places of 96 types in Kyoto City have this data. It's a good sample size to understand the temporal and spatial activity pattern of the city. Here is a comparison between our Wi-Fi data and the live GPT data at a famous tourist attraction. You can see that they present very similar patterns. As we all know, demand patterns might be dependent on topical issues, such as containing policies and lockdowns. Another dimension of information very useful is the reactions and sentiments of the public towards the policies. Google Trends can help us to understand how much a specific problem or policy is part of the public discussion. In addition, we want more information on people's sentiments, emotion, and attitude. A promising data source is Twitter. We create 2 pipelines to collect tweets based on keyword and location. We can see a peak of tweets about COVID in the middle of August 2021, which coincides with the so far highest wave of cases in Japan. Also, we notice increasing trends on travel and sightseeing, indicating some ongoing or coming recoveries of travel demand. Some topic and sentiment analysis are expected in the future, as well as data fusion of location-based tweets and mobility activity data. Next, I'm going to introduce our recent work and learning the impacts of COVID-19 policies from aforementioned data sets. We select a timeline from February 2020 to April 2021 to measure the restrictive and stimulative impacts of the policies on mobility and activity trends. We choose a regression model with time series arrows. I will not discuss much on technical parts of the model, but just noting some advantages here. It is suitable for time series data. It can eliminate serial correlation and estimates the magnitude of the impacts with less bias. The dependent variables are the demand indicators I introduced before, 6 from Google, 3 from Apple, and 3 from our own Wi-Fi data at 3 important locations of Kyoto City. For the independent variables, they are daily new cases. Here we consider the cases can influence travel behavior, so it's an independent variable. And the implemented non-pharmaceutical interventions, I will introduce how we use official policy period and Google Trends to create the variables for policy in later slides. And the weather, which are temperature and the rain, and calendar effects, which are dummy variables for holiday, weekend, and sightseeing seasons. Here are the key interventions in the selected timeline and after timeline. Two divergent policy sets feature the timeline of Japan. One is containing policies such as school closure, stay-at-home requests, and state of emergency. The other one is policies to revive the economy, among which go-to-travel campaign is nationwide and the most influential. It will provide discounts and coupons for travelers. These two policy sets are supposed to have controversial impacts on the mobility and activity trends. We exclude the effects of vaccination and the repeated implementation of state of emergency in this analysis. Next, I will explain how to use Google Trend to enrich the variable for policies. Usually we use binary variables to describe policy implementation. After day is within the policy window, it is 1, otherwise it's 0. However, Google Trends show that today when policy received most attention is slightly before the implementation period. It's usually after the announcement. We therefore hypothesize that people may conduct some self-restriction before the first day of implementation to get used to the policy. And after policy, people will not get back to normal instantly. So we extend the policy window and smooth the data as the red dashed line. And we use them as the policy variable. This might be true for containing policies, but for policies to stimulate travel demand, people may behave in a totally different way. People may decide to join the campaign after several days of public discussion on it. So we use moving average to process the data. Here is the estimation results of the model. We have a good model fits, and I would like to highlight here that the first implementation of emergency made a critical contribution to limiting the activity and mobility demand for all sectors. But the effect of its second implementation obviously faded away. Besides, go-to-travel campaign increased travel demand somehow, especially at second stage with coupons that can be shared among regions. Furthermore, we can notice that the categories like retail and recreation and the transit station receive more significant impacts from policies than, for example, grocery and pharmacy. And so as for the 3 places having Wi-Fi data, they also receive significant impacts because they are main tourist attractions and railway station in the city. Apple Index also sensitive to policies, but we want to note that they are based on the transport mode. The user search for pair of origin and destination using Apple Maps instead of a real trip. Here is the forecast results. The models has successfully captured trends for all cases, but just some underestimation on demand rebound in this April, which is a sightseeing season with no containing policies, so people can feel free to go out for sakura, the cherry blossom. Here is the conclusion, the limitations. I want to note the limitations of the study. So the measured impacts or coefficients from the model can provide insights, but are not easily transferable. As in particular, when in the forecast window, we have some events or policies that have been never experienced by the public. The decay of continuing policy due to repeated implementation, for example, the third, the fourth, the fifth state of emergency are difficult to predict. Also, the effects of vaccination can be complicated. It may contain the pandemic, but also encourage the mobility and activity demands. That's all for this study. And Jan-Dirk will introduce other ongoing studies within this data-driven domain.
Thank you, Wenzhe, for introducing our study. I want to conclude with some general comments on other activities related to the aforementioned DALUMA project. So we aim to extend the models presented here by utilizing also some of the other, also already aforementioned data. Firstly, I should say that we try to fit those forecasts not just to Google mobility trends, Wi-Fi data, and but instead also to what we might call more objective and absolute numbers in terms of data that we have obtained via mobile phone statistics of how many people are in which mesh in the city, as well as we might do that related to traffic flow counts that we also have for selected places in the city. But then we need to infer the activity types, which we are nicely being given via these Google mobility trends. For this, the Google Popular Times data that we have for some of the points of interest in the city, again, we think might be very useful. We also mentioned the Twitter data. Here, I think what we are currently doing is we estimate topics which relate to, which therefore show us the trends in the of what are people concerned about in the city, as well as sentiment analysis, which tells us something about whether, for example, the number of tweets that have a concerned character, that have a fearful character, have increased or decreased over some time. This, again, we suspect has some vague relation to mobility patterns, and therefore might help us to give some predictions as to activity levels in the city. We can also from this, we further need to advance then, if we especially have spatially more disaggregate data from regression models to deep learning models. We especially want to consider that there is a relation between different places in the city, as well as between different time intervals. And we mentioned here the importance of time lags in this presentation already. This leads me to some final general concluding remarks. So we showed here an effort to disentangle the different policy impacts. And we discussed the difference between enforced and not enforced or unenforced COVID-related mobility changes. We also discussed about gradual versus very rapid changes. And we also discussed that actually some of these differences remain quite vague. So that, for example, restricting policies will also have an impact beyond the time period over which the restrictions are enforced. The presentation furthermore highlighted the possibilities of various newly available big data. Where we think we're still struggling with is still capturing really those unenforced trends. Can we really extract trend makers in terms of that trigger mobility changes, especially those unenforced mobility changes? We mentioned here again the Twitter data and the Google search data, but to do this, we feel we need more on a spatial disaggregate level to really achieve better predictions. Finally, I just want to mention that, of course, this goal of Daluma to predict mobility patterns is impossible. So what I mean is, if we would have a perfect prediction, then of course people would react to it. It's like predicting the stock market. Once you predict it, you become a player, and therefore people will react to this player. Nevertheless, we should try to achieve a better forecast. And I want to conclude with mentioning that since COVID is such a worldwide crisis, and since we have nowadays these various free, or at least partially free data, such as the Twitter data, for example, such as these Google mobility trends that we used here, we think there's a large role for comparative studies between cities. And we think that actually through this crisis, we can learn much more about what defines and what makes cities resilient. And with that, I want to conclude, and we're looking forward to your questions. Thank you very much.
예, 감사합니다.
Thank you very much. It was a very long presentation, and it was about COVID-related research taking place in Kyoto, Japan. And I think 22 months has passed since the outbreak of COVID-19. And during that time, what kind of changes have taken place in the mobility pattern? It's a long-term analysis.
체인지 데이터라.
You have used Apple data, Google mobility trend, or popular time data, and Twitter data. These were the data that you have used, and also Wi-Fi data were also used. Long-term basis, as COVID-19 prolongs, yes, we need to once again carry out more studies. As you know, diverse policies were implemented like stage 1, stage 2, 3, 4. And I believe that in Japan also, there were diverse stages of the different policies, like you had restrictive policies, but also stimulus policies, and you have categorized that as enforcing policies and also unofficial or unenforcing data. And you try to understand the impact of these policies. You try to monitor that through statistic analysis. You try to come up with the future forecast and what kind of policies were most effective. So your studies and research were quite interesting, and this project was called with the acronym of Daruma, and I hope that further studies can be carried out. So I believe we can have more discussions during the panel discussions. Now's the time for a panel discussion. We are inviting 3 discussants. So we have with us Professor Kim Tae-hyung from Seoul National University joining us virtually. And let me introduce the second panelist. We have with us on site physically Professor Park Sang-shin and Professor Lee Im-pyong from the University of Seoul. So starting with Professor Park Sang-shin, I'll be giving you 7 minutes. So we must conclude by 3:30 p.m. Korean time. So give your own view, and the remaining 3.5 minutes, you can pose a questions to either Yanda or Jan-Dirk or Wenzhe, anybody. So Professor Park.
서울시립
Hello, I'm Park Sang-shin from University of Seoul, and I'm from the Graduate School of Public Health. I would like to make a few comments. Since last year, outbreak of COVID-19, well, we can see that a lot of other types of respiratory infection has gone down, but norovirus at the specific age group has gone up dramatically. And because of COVID-19, the overall infectious disease has gone down in number, but it has made a prediction of future outbreak all the more uncertain and difficult. And the presentations made by today comes at a very opportune time. And I'm sure thanks to such efforts, things will get better, but we still have to be on our toes. And the epidemiological technology has advanced greatly these days. In public health and epidemiology, well, compared to chronic illnesses, infectious illnesses has received less attention and less support. But with high technologies, there has been a lot of advancement, along with advancement in vaccine development. So not just for the infectious disease, but overall technology will help us overcome and prevent various diseases going forward. And the disease burden on cities will be reduced as a result. And when we look at the spread of COVID-19 in crowded areas like karaoke bars, we are seeing some outbreaks. And I think this COVID-19 will also affect construction technology and architectural design. Well, many people think this could be the end of infectious disease, but with aging of population, even before COVID-19, we were seeing an increase in the number of infections. So especially, but of course, the respiratory infection will go down. But as I've said before, in the post-COVID world, nobody can tell what would happen just around the corner. Last but not least, when it comes to in the COVID area, we are exercising less and less, which increases the risk of chronic illness. And there are certain things that we can do in an untact manner or things we cannot do in an untact manner. As for working and learning, we could do it in an untact manner. But, working out, exercising in gyms cannot be done in an untact manner. And the most important challenge we face in our daily life was how to exercise. And in line with the spread of other infectious diseases, increase in prevalence of depression, and up until now, we used to have a lot of indoor exercise environment, but in the untact area, we have to find various ways to increase our exercise in the indoor space, and that would be very essential in our life in the metropolitan cities. In the future, when we think about post-COVID era, there will be a lot of paradigm change, and there could be a public health care crisis at any time, and we should be prepared better at the government and metropolitan area. We should have a crisis prevention and crisis coping mechanism. That's all I have to say today. And the presenters have made wonderful comments, and I would like to share some of my ideas and questions. First, Professor Lee Heechung has talked about the people's movement and mobility going up in certain areas. And I'm studying the impact of social distancing on infectious disease in this with COVID era. And I was very much interested in Professor Lee's presentation. And the speakers from Kyoto University talked about the methodologies, and they have explained the actual trends. And that was very helpful for my own research as well. And Dr. Anda, in epidemiological study, there are people who refuse to cooperate in epidemiological studies. But Dr. Anda has offered us a tool that we could use right away for epidemiological investigation. And Professor Park and Professor Lee, I have a question as well. Sometimes infectious disease can spread through transportation, but we can think about multi-level. For remote distance, transportation could be the area hotspot for mass spread, but even when people are gathered together, there could be a hotspot. So we should have two-level decisions, and I'm sure Professor Lee has done some related research as well. Physics is the foundation of all natural science, so I believe we might find the clue in physics. Professor Park has talked about toy modeling. Do you have any ideas about how to prevent the spread of infectious disease? I have no idea, to be honest, because models have limits. And if we don't use mask in a bus, all we know is that virus can spread in the bus. And Professor Lee Seung-jae has also proved that mask is very effective in preventing the spread in a bus. But model inherently has its own limitations. And continuously refining the model to make it more realistic is actually very important. We could model buses, taxis, and subway trains and identify how fast the COVID-19 will spread, how far it will spread in remote traveling. That could be helpful for public policy making.
잠깐 말씀드리고 사실은
Well, I will briefly mention, you talk about two-level, and in case of two-level, we have macro and micro level. In case of the macro, we use it to forecast. We use Kalman technique. For example, 1 week from now, how many COVID confirmed cases will there be? We forecast. And also we have candle chart. This is similar to the stock market chart. Very similar way we analyze. And like 1 week trend, 1 month trend, or 3 months trend, we use app, and then we try to show which area has the greatest number of the confirmed cases. So together with the credit card usage, well, the places where there are a lot of credit card usage, that means that there are confirmed cases, many, and then it's a dangerous area. And if there are not many confirmed cases, that means that there aren't many people gathering, then we try to attract more people to come to that area. I didn't make any presentation, but according to, well, my paper was published in the Science, so please look at my paper later on. We don't have much time, so let's hear Professor Lee In-pyong and also Professor Kim Tae-yong. So Professor Lee In-pyong, please go ahead. Hello, everyone. I am Lee In-pyong from the University of Seoul. Thank you very much for organizing today's forum, and also thank you for the great presentation given by speakers. Before COVID-19, we've never experienced things that we are now experiencing, and we are witnessing the policies that are being implemented never before the COVID-19, and now's the time that we have reviewed the policies that we have taken. Well, spatial engineering is my specialty, and spatial information area is my main interest. And among the four speakers, Professor Park Inkyu I enjoy very much your presentation, especially toy modeling of COVID-19 spread and global urban digital model. I'd like to make a few comments. Well, based on the big data, we can analyze the big data, and there are diverse kinds of the big data for spatial information, big data, and I am in charge of providing spatial information data. Professor Park introduced SMAP, and if you look at SMAP, 25,000 of the aerial photos were taken, and more than 600,000 buildings were actually built and analyzed. And you have built this SMAP. It's very expensive, very difficult to do that, and it keeps changing. Well, we do this, but tomorrow a new building can be built. So, in a way, these the most important, like a backbone of the data, keep changing. Because of that, challenges are increasing. In the past, once a year, probably we have taken the aerial photos, and using the aerial photos, we use that to update the spatial information. However, as the things change so rapidly, in my specialty, what we are pursuing is that the changes that are taking places, we try to reflect those changes in a real-time basis. So cloud sourcing, all kinds of sensor data are also being deployed. For example, you all have a camera, right? Embedded in your mobile phone, and you take photos. So we can use that photo as well. And even though it's not an autonomous driving car, still there are black box installed inside a car. As the cars drives from one place to other places, they gather image, and we can use that data as well. As time goes by, there are a lot of drones will flying on sky, and drones will also take all kinds of data as there are sensors installed in drones. And in case of communication, because of the communication revolution, we have 5G, but probably will go into the 6Gs and on and on. Once again, the remote sensor will play pivotal role in gathering the data, and then this data will be delivered to the central room, and on a real-time basis, we can monitor the urban cities, we can detect the changes that are taking places, and based on this, we can update the spatial information once in every few months. So the real-time changes that are taking places, like spatial big data, as you mentioned, the GUMD or digital twin or the metaverse, I believe that definitely can play important role. And upon listening your presentation, the first and the third you talk about, during the COVID-19, we need to monitor what changes can take place after the COVID-19, especially not only monitoring after COVID, but also before COVID similar event. You need to also do the simulations to come up with the most optimum solution. So in that sense, global urban digital model can also be utilized. Upon listening Professor Park's presentation, there are a couple of questions that I'd like to pose. First, to Professor Park. The global urban digital model, and we used to call this a digital twin, or sometimes we call this a 3D spatial model, or sometimes more recently we talk this as a metaverse. So all kinds of discussions are being carried out, and when we do this, sometimes we perform much less than our expectation. Is because we are trying to come with a universal model that can be applied everywhere for everything. And we spend a lot of money, but it's not applicable and we don't see benefits. So that's why no matter how well we prepare this model, it doesn't work well. So instead of coming up with a universal model and that covers a wide area, we try to narrow down the scope, and also instead of the universality, we try to come up with a local model. So when it is operated effectively and efficiently, then we can develop it further. That's what we are doing. And in light of that, within a limited space, do you have any specific examples that you have? And since I don't have time, I'll ask another question to Professor Lee Heechung.
It was interesting, but he talked about London, California, and we thought that each country had different response to the outbreak in comparison, but there was a lot of similarity across countries. What kind of difference did you see between countries? And last but not least, to Dr. Anda, mobile phone signal data was very interesting, and he has offered the trajectory enhancement project as an example. But do you have any other example of using mobile phone signal data for any other usage? So can you share other examples? Thank you very much. And we are running out of time. So Professor Kim Tae-young, could you share your ideas? Yes, I'm Kim Tae-young from Seoul National University. And this session would have to conclude in 5 minutes, so I have to be very concise. I came up with questions, but other professors, other discussants, I would like to ask other discussants to answer my questions if they think it's relevant. Dr. Yanda and Dr. Wenzhe, restricted mobility, and after COVID outbreak is subsided, the mobility increased. It was a cycle, and policy intervention really had an important impact. In this case, in the initial phase of COVID-19, people did not move around, and tourism was very much declined. But now they're trying to boost the tourism for economic stimulation. So could you be more? Could you be more? I'm very much interested in the specific impact of policies. Could you elaborate on that? And Dr. Anda, you have talked about the possibility of this mobile data in combination with sensors and the purpose of trip. And these days, the pedestrians' attitude, psychological factor is also an important part of transportation planning. So how did you factor in all that? Can we factor that in your model? Can you talk about the possibility? And regarding Professor Park In-kyu's presentation, urban physics is a rapid up-and-coming field of discipline. In my opinion, physicists' scope is expanding. And what's the role of urban planner what kind of synergy effect do you think you can create in working with urban planners, especially when it comes to complex systems? Marx Weaver has talked about bounded rationality. So in modern rationality, it's based on modern rationality. And do you think we can see some paradigm shift? And last but not least, to Professor Lee. And there is an international joint research project going on led by Professor Lee. And Professor Lee, how do you think urban planning is responding to pandemic in terms of residential, shopping, and leisure space? So can you do overall prediction and explanation? In carrying out international joint project, we carried out a survey in large cities, and in October of last year, we had the first survey, and the second survey took place this year at the end of October. We expected that there will be natural healing effect, natural experiment effect. By that, the number of confirmed cases we expected will decline drastically, but that did not happen, which is regrettable. But in the case of Seoul, in religious communities where large crowded area, people still thought of those places as highly risky, and the overall awareness of people in terms of infection is similar level to that of last year. The average is same, but the deviation has declined significantly. Compared to the past, the number of people who perceive high level of risk are now seeing less risk. So on average, it is same, but it is being converged now. And what kind of negative impact COVID-19 has had on our activities? Well, there is a variety of impact. Pandemic is predictive, and our freedom is restricted, and social media is spreading fake information, and social demographic characteristics lead to different outcome like gender, income, and I would like to talk about several implications. First is we need study at the subgroup level. And then there is conflict. Increase in online activities, remote working. We have also seen increase in social media and delivery, and the level of conflict is not receiving fair amount of attention. And Professor Lee is leading an international joint research, has discovered all this fact. Ministry of Health has, in January this year, has launched a psychological health support team and has created a working level body in September. And families tend to have positive impact on reducing depression, but family conflict actually increases the anxiety level greatly. Such conflicts between neighbors and families need to be studied further. Thank you very much.
의견이신데
Thank you very much. Well, it's over the time. It's 3:32. I wish I could have 10 additional minutes. We are behind the schedule. And we have with us Professor Anda and Professor Anda's take. So, Professor Anda.
the comment for your question or comment. So you have only around less than 5 minutes, so you can comment on it.
Okay. Yes, thank you very much for the questions. So what are other use cases aside from the one explained to monitor the spread of virus 19 when we have mobile phone data? I think it's one that is very useful is about transport planning, since we have the evidence of how people move. We can understand, where is the travel demand, and then things that, for example, transport agencies are very interested on is on knowing that if we are going to change something about the city, for example, there's going to be a new residential area created, how would the mobility of all the city be affected? So to answer this question, you need data, and then you also need to couple this with, for example, a digital twin model. And it's some of the areas that we are currently exploring in Eraspark. Then to answer quickly Professor Kim Tae-young's question, I actually think it's a very difficult thing. So in the mobile phone data, we have the evidence of how the trip happened till a certain degree, because that's actually the effort we are actually doing now. We want to improve.
Professor Anda, could you lower your computer's speaker's volume?
Jan-Dirk,
Yes.
did you catch the comment or question?
Okay. Yeah, and just to finish.
Professor Anda, you have to reduce the volume on your computer. We are hearing very strong echoing. Can you reduce your speaker, because we are hearing the echo of your voice?
Hello, is this better? Yes. Okay, sorry for that. Yeah, just to finish my idea. I mean, when you have mobile phone data, you see how the trip happened, but you don't know anything else. You don't know, what are the motivations of the people doing that trip. And hopefully that's something that we can look in the future, helping us with, for example, discrete choice models to understand, what would be the motivations for people doing certain trips. And that, of course, is useful because then that helps into, for example, if we want to run simulations or we want to see different what-if scenarios when there are changes in the city, then we need exactly to understand, the motivations behind those mobility patterns we see in the mobile phone data.
Yeah, actually, we need more time, Anda. Yeah, because we need more time to learn about your approach, about how to combine the household survey data and mobile data, because they have a different aspect. So maybe we have another time to discuss in detail. Okay, thank you very much for your discussion. And Jan-Dirk, can you hear me?
Yes.
Yeah. Can you talk more about Daruma project?
Okay. Yes. Thank you. How can I switch off here? Can you hear my echo?
Yeah.
It's okay.
Yeah.
Okay.
I can hear you.
Okay. I can hear a lot of echo here. I don't know how to. Maybe. Okay. I try. Yes. So this Daruma project the idea is the deep learning or the anticipating urban mobility peaks. It's a collaborative project with universities in Munich, Budapest, Madrid, as well as with the AI group of Hitachi. And so what we presented here today was kind of a first step where we use some of the data for a regression model. We want to advance that more, and that also connects to one of the questions we got, to get indeed more profound insights into the effects of these different policy measures in spatial level as well as by time. I think a general comment I want to make is that one of the main difficulties, and what we really, of course, want to know for policy making, is transferability of these findings. But I think that is really the challenge. So we could estimate here parameters. We could estimate here parameters for Kyoto in terms of how much leisure trips, in terms of how much shopping trips, in terms of how much work trips reduced. But how much are these parameters transferable to other cities? For that, really, we need these comparative studies, and that's something that we try to do with the Daruma project by comparing at least 3 cities here in detail.
Okay, yeah, maybe we also need more time. Maybe you can making another time to discuss more and learn more
I hope so.
from you.
Yeah.
Okay, thank you very much for the speaker from the overseas, and you have really past the time, but you can have only 2 minutes. Yeah, 이정 교수님, 박인 교수님 2분 정도씩만 저 얘기 좀 해주시죠.
So Professor Lee and Professor Park, I can give you 2 minutes each. So let me answer the question. The difference between Korea and overseas cities, I can think about 2 differences. And of course, there clearly is cultural difference and individual preference and consideration for other people that can have an impact on social system and spread of the infection. And I think there's also a difference in technological infrastructure. Korea has a lot of IT advanced infrastructure for smartphones and digital technologies. So controlling infectious disease in Korea or even other advanced countries like the US, Europe, Japan, they have different infrastructure. Of course, we have different ideas of privacy issues and ethical issues, and the cultural impact also plays in here. So technology and culture seems to have an impact on how the cities control and accept the social distancing measures. Of course, there's the commonality of the humanity and the trend in the industrialization era. It has created urbanization with everybody coming into the cities, but now we are seeing another decentralization within the metropolitan area. So it's focused more on local areas, creating decentralized structure. I think it is common across all metropolitan areas.
예, 저도
Yes, I'll be very brief. And Dr. Anda and also Professor Jan-Dirk, their presentation shows us how well we can apply and use various kinds of the data to understand the effect of the policy. In case of physics, there's a saying, I'm sure that you heard a lot about quantum physics, right? There is a certain phenomena, especially within the social phenomena, when we see with our own eyes, that phenomena has already changed. So it's already gone, which means that whenever we try to focus the future, it's already happening. So that's what I want to say. Utilizing social data, there are a lot of limitations and restrictions. So I hope you can understand that. The modeling that I do, we try to focus the future by applying the model, but definitely our focus can always be wrong. So nonlinear, impossible to predict is something that we try to see the future. But what I'm trying to say is that humans' policy can always change the landscape of our world. So that's the message that I want to tell to both Dr. Anda and to Professor Steak. Thank you. Thank you for your presentation.
감사합니다.
Thank you, Professor Park. Well, 1 hour and 30 minutes flew by. We have so many things to talk about, so I would love to invite the 2 foreign speakers next year again. But before that, I hope we can communicate via email for some kind of joint research. So I would like to thank everybody for joining us today. Bye-bye.
Very much.